In this video, we are going to look at how insertion operations can be performed in a binary heap. So, as I discussed in the previous video, we can actually use an array to store the numbers of a binary heap. Suppose that I have an array where I am using it to store the numbers of a binary heap. So, let this be my array. Okay, so which has indices 0, 1, 2, 3, 4, 7 and 8. Okay, now suppose that I need to insert these numbers, let's say 10, 25, 3, 1, 2, 7, 40. Suppose that I need to insert these numbers, and I'll explain the procedure one by one. So in the previous video, I have said that we'll be only considering the min heap to discuss the algorithm. The same kind of algorithm can be extended to the case of max heap as well. So first we are going to insert the number 10. So the number 10 will be at the first position of my array, and if you consider the same structure in the form of tree, then the number 10 will be my root now. Then you have to insert the number 20. So I'm inserting the number 20. So here the 20 is written. So the tree will be always growing as a complete tree. So I will not go to the next level until the previous level is filled, and we will be filling the numbers from the left side to the right side of the tree. Now I am going to insert the number 5. The number 5 will be at the third position, or at the second index of my tree. So this is number 5, but you can see that there is an obvious problem here. That is, because this is a min heap, the value of the root cannot be more than the value of its child. So what we will do is we'll compare the value of 10 and 5. So here we are seeing this number is less than the value at the root, so we have to make a swap. So in order to make the swap, this number has to find what is the index of its parent. So I have said one equation for finding the index of its parent. So if I is the index of a child, then if you find this equation, that is I minus 1 by 2, then if you take the floor value, then that will be the index. So here the value of I is 2, because the number 5 has an index 2. 2 minus 1 by 2, which is 1 by 2. Now if you take the floor value of 1 by 2, the integer which is less than or equal to the value, that is 0.5, is if 0.5 is the number, then the index will be 0. So my index is 10, which means that, sorry, my index is 0, which means that the number is 10. So we had to make a swap between number 5 and number 10. So I will make that swap here, swap operation here. So this 10 has to be taken out and this 5 has to be taken out. Then we have to make the swap. So 5 will be here and 10 will be here. So I will have the same kind of rearrangement in the tree structure as well. So 5 goes here, then 10 goes here. So in order to represent a binary heap, we just need an array. We don't need to define any pointer or a data structure or any structure which has pointer to the next node. Nothing of that kind is required. Okay, now we have to insert the number 3. So obviously we'll go to inserting the number at this position. So if you represent it in the form of a tree, so 3 will be at this position. Now this is not a binary heap, so we have to apply the same equation to find the root, then compare, then you repeat the procedure. So here the value of 3 is at the position number 3. So if I find the index of the parent of the new number 3, then 1 second. I'm removing this one. Now if you want to find the index of the parent of the number 3, then the index of number 3 is again 3, so this will be 3 minus 1 by 2, which is equal to 2 by 2, which is equal to 1. This is an integer value, so there is no need to take the floor. So the index is at 1, so I will be swapping the number 20 and number 3. Okay, so number 3 will be at this position. Let me erase that out. So number 3 will come to this position, and number 20 will be at this position. Okay, now there is again another problem, so I will draw that here also. So the number 3 will be here and number 20 will be here. So here also there is a mismatch. This is violating the binary heap property. So I need to swap the number 3 and number 5. So the index of the parent of 3 will be, this has an index 1 minus 1 by 2, which is 0, that is at number 5, the index 0. So I'll be swapping the numbers 3 and 5. So I'm swapping the numbers 3 and 5. Excuse me. So this is 3 and this is 5. So I will have same rearrangement here as well. So this is 3 and this is 5. Now this is a binary heap. Now let's insert the number 1. So you can see that the number will be inserted here. Then so in this case the number 1 will be inserted here. So number 1 is less than number 5. So number 5 will be taken or swapped with the value of 1. So I will have 1 here, then 5 here. Then we will be comparing these two values. So 1 is less than 3. So I will take those two values for swapping. So this will be 1 and this will be 3. So there will be similar rearrangement in the tree structure as well. I am just removing everything, then drawing the structure of the array here incomplete. Okay, so I will have 1 first, then 3, then 10, then 20, then 5. So I just need to write the order, that is 1, then 3 and 10, then 20 and 5. Then I need to insert the number 7. So I will be inserting the number 7 to the left of 10. Okay, so there is also so 7 will be here, so there is a violation. So I will take this 7 from this position, then I will swap it with the number 10. So 7 will be here, 10 will be here. Now if you look at the number 1 and 7, this is actually matching. There is no problem with this arrangement. Then we will go for inserting the next number, that is 40. So 40 will be, so before that I need to rearrange these numbers that we swapped in the tree structure, but we didn't the same for the array representation. So I will have 10 here and I will have 7 here. Now we are going to insert the number 40. So the 40 is the largest number, so there will not be any mismatch with its parent element. So this 40 is obviously greater than 7, so it is at the correct position now. So this is how we perform the insertion operation in a binary heap. I hope it is clear. Thank you.